let's go. So in our introduction, we want to introduce innovative Android-based systems. So we are using the Vuzix for our design platform, but essentially this can be used for any kind of Android system that is Android 5.2. Essentially, we want to create a system that could help users with their daily life. So let's say you are in a foreign country and you want to ask a question to a foreigner, but you don't know what their language. So you can just say, okay, I need to go this way. What can you tell me which way I'm supposed to go? And it will be able to tell in future iterations. And the SmartGlass is transmitted visual data to LLM for analysis and receive an instant output that can be assisting the users. So let's say you're sitting down and say, okay, what am I looking at? And it will tell you that right now. So what's next? So our motivation, like I said, Pan, he wanted to make a design like this, and I helped him on how to build this system architecture and the software point of view. It is a quite innovative design, and it's quite cheap compared to other, products out there like the Google Glasses and Apple Vision Pro. I mean, they go for thousands, right? So we want to make it simple and innovative at the same time, easy to transfer to different programs.
Okay, so the background of this project lies on two different disciplines. The large language models these days, they have changed our lives dramatically. But the computational capacity limit on small wearable devices like smart glasses is a problem when this model is integrated into it. And so unlike smartphones, smart glasses is a hand-free option when it comes to scenarios with high mobility requirements. And the integration of large language models with a device with a high mobility potential brings further values to the industry. So we have researched several different related works and options, both in the academia and in the market. The gaze track by Cornell University is not a smart glasses by design. It is a technical demonstrator that focuses on gaze tracking. It is a system based on acoustic signal, unlike many options on the market that uses artificial intelligence and cameras, which is more power efficient and less computationally intensive by its nature, which is an evidence of our approach that can be feasible in the future. So from a market perspective, we have Apple Vision Pro by Apple that was recently launched into the market. But the whole system is it is designed for stationary use. So even in the video of like the marketing video of Apple demonstrates the users to be stationary in the sofa or in an airplane. It has a standalone battery connected to the lens through an external cable. And even with an external standalone battery, it can only reach around 2 hours usage. It is also powered only by Siri, which is not a LLM assistant. There has been rumors about Siri will become LLM powered by 2026, which is a long time from now. We also have Meta glasses by Meta. It is designed for mobility. It has built-in battery, which achieves 4-hour runtime. It is also Meta AI enabled, but it is not designed for industrial settings. We also have a Google Glass, which was canceled like a long time ago. And it is designed for mobility. It is only 38 grams in weight. There has been a demo video recently that showcases a SmartGlass from Google that is Gemini enabled, but further information remains unknown.
Okay, as for the system design, our system consists mainly of three parts. Our smart glasses and our backend server and the local computer who's running the large language model. And this is the activity diagram. I hope I'm right. Sequence diagram, I'm sorry. And I'll explain this diagram really shortly. So firstly, you'll see the user actually takes a picture and record the voice prompt from the smart glasses, and then the smart glass will send the data to our backend server, which will process the local data into the text data that the large language model can read, and then send this text data and the image to our local computer, which is running the large language model, and then language model will give a response according to the data that it got, and then this response will be sent all the way back to the front end and presented on the glass in front of the user. And our system mainly consists of three parts. First part is two parts actually. First part is the smart glass system, which can be any glass, but in this scenario we use the Vuzix. And the second part is the web server and the local computer, who's capable of processing the large language model and coping with the data transference. And we did run some tests to test the performance of our current setup. So as for the current situation, the whole workflow was designed for a single client, which means a single device. You can see that while there's a one device scenario, the throughput is rather small. This is because of the nature that how we designed the experiment. So the time will be recorded at the beginning of the whole process, and then whenever there is a file got inputted to the server, the time there will be a computation done with the past time, and the file uploaded. So you can see that when there's 10 devices, the throughput is just exploded to a very high degree, and it's actually not a good sign in this kind of situation, even though we probably want the throughput to be as big as possible. Because in this kind of scenario, the system will probably get overloaded, and it will be not able to operate at all. And then you can see the average latency of our system. Again, this is at this stage only designed for one device, but you can see the processing time of the large language model latency decreased at the 10 device, which is kind of unexpected. But I can explain that because the large language model was actually cut it off from its previous processing with a new prompt. In the 10 device or multiple device scenario, which means it hadn't even finished the generation of the previous prompt. Then another new prompt came in, so it had to start processing the new prompt anew. So that's why you are saying the 10 devices latency is actually lower than when there's one device. And after that.
Okay, so as we said, the main design principle of this project was to have a computer-to-peer network. The main limitation is that because of the limited time and device protocols, so because we're using a baseline Android system, the web server we were able to use was just a proxy server. We don't actually use it, but because we don't want to expose our main server, which is being his computer, we had to go with the process, because to get a proper running LLM on a AWS EC2 instance is pretty challenging, especially expensive as well. So we have to get a lot of credits and all that stuff. So, but for the future iterations, we're going to be doing a pop-up system that actually going to have an individual broker that we'll be building. So AWS will be working as the broker itself. So rather than using it as a proxy server, it will be actually a proper broker, which will handle the data communications as well as the node communications as well. So that way we can do multiple parallel processing. As you guys said, we'll go back to the. So from the average latency, the reason why we had this metric is because we want to see the system behavior and how fast it is. The main limitation of these kind of systems is the LLM has to get a request and send a response, and this slows down the whole process. You usually want to have like an embedded system that has the LLM built into it, but because of the Vuzix, we can't really do that. But as the 10 devices showcases, it's lower. That's a lie. The system just gives you the final output, but because we're using a peer-to-peer network, it actually just replicates the response of the last processing. So actually just behavior is odd for that purpose alone. Like I said, once we have the peer-to-peer POP-sub system that with the broker, we'll be able to have multiple processing nodes running with the master-slave behavior. So we can actually have up to, let's say, 100 that usually have the throughput is pretty minimal at the level with the EC2 AWS system once you use like the macro 64-bit system. So that's the idea for us, and we'll probably be implementing additional LLM networks to improve our image processing. We can get more API connections as well. So that would be the future works.
Okay.
That's it for us. Any questions?
Okay. All right.